Preview video, solving systems of equations with the substitution method. Recall that a system of equations is when you have two or more lines graphed on the same coordinate plane. The solution to a system of equations is the point at which all of the lines, or in this case both of the lines, intersect. We want to learn how to solve a system of equations using a method that does not require graphing. We've substituted values before, so if you were given this problem, given the line 2x plus 3y equals 11, find y when x equals 4, we could simply take our 4 and substitute it in for the variable x. We're allowed to do this because we know that x is the same thing as 4. So instead of writing x, I write 4, and now I only have one variable, so I can solve for y. And I get y equals 1. This tells me that given this line up here, when x is 4, y is 1. In other words, the point 4, 1 is on the line, or a solution to the equation. Now we're going to see what happens when we substitute an expression instead of a value in for a variable. Let's solve the system of equations. The system of equations is 2x plus 3y equals 4 and x equals 2i minus 5. Those are linear equations, so their solution will be the one point where they intersect. So far we've only done this by graphing, but now we need a method that does not require a graph. This is particularly important because sometimes it is hard to read a solution on a graph, especially if it's a fraction or decimal. In the second equation, I see that x equals 2y minus 5. This means that I could replace any x I see with 2y minus 5, the same way that in the previous example, we replaced x with 4. I'm going to copy down my first equation, but instead of writing the variable x, I'm going to write the expression that's equal to it, the expression 2y minus 5. The advantage to doing this is that I'm now left with only one variable, and I can solve this equation because when there's only one variable, I can solve for that variable. I first distributed, then I combined my like terms, and I used inverse operations to get y equals 2. Now I'm not done yet because I know that the point that these two lines cross is going to be an ordered pair, and I've only found that y equals 2. But now I know that I want to find the x value in both equations when y is 2. So it doesn't matter which equation I choose, and I need to put 2 in for y to find x. I'm going to use the second equation because it looks easier for me to find x since it's already isolated. I've rewritten my second equation and I've substituted the value 2 in for y. Now I can find x. And I get x equals negative 1. This tells me that the solution to the system is negative 1, 2. I should be able to take this point and put it into both the second and first equation and have it come out true. You can even try this on your own. Also, if I were to isolate y in both equations and then graph the two lines using the slope and y-intercept, this would be the point where they both cross. So let's summarize. Rather than graph the two equations to find where they cross, I decided to take the expression that's equivalent to my variable, substitute it into my other equation, leaving me with only one variable left so that I could find the value of one of the variables in my solution. I used that and then substituted it into either equation to find the value of my other variable, in this case, x. And I found that the point negative 1, 2 is the point where the two lines cross, the solution to my system. Thanks for watching. This was just a quick preview, so don't worry if you're still confused. We'll go over plenty more in class.